Hello and welcome. I'm Shadow of Shadow Gaming, bringing you Programming with Shadow, episode number 57. In today's video, we're going to look at insertion sort. So, insertion sort is another n-squared algorithm, so go ahead and spoil the surprise. It's going to perform on similar levels to the others, but in general, it's only n-squared in worst case and average case. In best case, it'll perform very similar to the bubble sort with the optimization we did. So we'll go ahead and implement it, and I guess I've been talking about it first. Let's do that first, I guess. Let's make a new file. I can find add. Let's add a new item, insertion sort txt text file. All right, let's do an example. We'll do some values. Here, where's selections? Let's grab these values here. This one, the algorithm's a little different, or a little different in how it works, but it's still n squared. So what we'll do, we'll pick the first position here, and we'll use it as a I'm going to say key. So we'll say key equals 3. So we'll pick a second index of the one before it. So I equals 1, j equals 2. And now we'll say, okay, so while we're in this situation, is that right? Start at 1, j equals 0, sorry. So it starts with the first position. So yeah, there we go. That's right. So what we're going to do now, so on the first thing we'll do, we'll say if the number at j is less or is greater than the key, then we'll take the yeah. So we'll say, okay, so we've got these values. So j is less than the key, so we'll set j to, we'll subtract 1 from it. It becomes -1. Let's do it in a different line. I'm trying to think how best to demonstrate this. So it becomes -1. Then we stop looping. Here we'll have 2 loops. We'll have an inner loop. So we'll stop looping. And now, because we're done, then we'll do the swap now. So now we swap these two. So now we'll increment I. So let's do I equals 2, key equals 4, j key equals 4, and j equals 1. So now we're ready for the second pass of the loop. So now we'll check these values. So we'll say is the value at j 5 greater than the key, which is 4, and in this case it is. So we will decrement j. So here we check again. This time we'll check the key again. It is not greater than 3. So this time we'll just break out of the loop. And now we'll do this swap again. This time we'll swap the position at j plus 1 and the key. So there. We'll swap those two. Yeah. Yeah, I feel like I'm doing something wrong, but I think I've got the algorithm, but I feel like there's still a problem. But now we'll get I equals 3, E equals 1, J equals 2. We'll continue looping through. We'll check these two. It's smaller, so J is here. Okay, so we're checking that these are smaller, so we'll have to move this one. Okay, that's what I'm missing. Here we didn't have a good example of this, so now we'll swap this one, swap this one, and J becomes that. Then we'll do it again. Now we compare this one and this position, and now they swap again. J becomes 0. Then we swap the last two, and now it's sorted. There we go. That's what I was trying to do, and what wasn't working on before. The numbers I picked here don't actually work for the algorithm. So let's do it again. So now the new value is I equals 4, which is the end of the thing. E at this point is 2. J equals 3. Now we just work our way down, so these two swap. And you can see with these operations here that it's becoming n squared very quickly. And at that point, we're done. And at that point, the array is sorted. So that was a bad example. I think this one will actually be easier to see in code, where selection sort was easier to see here. So we'll go ahead and try coding it next. Let's go ahead and create a new file, a new, not whatever I just clicked. Try that again. New class. And we'll say this one is insertion sort. Basically, we're just sorting it or inserting it into the correct position in the array. Public, static. No, there's public there. It could be static too. Okay. So here we'll do public, static, void, sort, int, numbers. And we'll do the other version with a comparison. Int sort with comparison. Son, can't spell. Long comparison equals 0. Return comparisons. Should be a long. All right. So let's begin. So I guess let me grab the bubble sort here. Let me grab this comment here. We'll fill this out as well. Sort. Here, we can go ahead and close some of these unnecessary ones. All right. So we'll be filling this out. I'm surprised these are going to be the same cases. This one will be gone. So it'll be like this. So again, we'll look at that at the end here. So let's begin. So the first thing I want to do is get an I. So I'm going to do it like this. For int I equals 0. I, that's what I want. All right, so there's us an I. So then my algorithm, I used key equals numbers at I. So we get that position in the array. Now we'll have a J. Let's see. I want to do it. Let's do it like this. Let's see if this works. That may not, but I'm thinking it should just be a while in this case. While J greater than or equal to 0. Now here's where we begin swapping in the insides. So that as you go down through the array, it'll keep swapping the value, so it inserts it into the correct spot. J minus minus. However, there's a problem. We need to actually do the check. We don't want to do this every time this is the case. We want to do it when the values are bigger. Let's add a snippet, surround with an if. So the if will be numbers at j is greater than the key. I think. I'll have to make sure that actually works, but I think that's what I want. And else break. Here, let's do a break like this. I'm trying to decide if I like that style. I'm still not convinced. Now let's do numbers j plus 1 gets the key. So we're not. So this should be it, and that's not a lot of code. So if this works, this should be all we need. So the first thing you can note with this algorithm, I'm not actually using my swap function. We're just swapping the values as we go, and we're just keeping track of what the key is. So we put it at where it's supposed to be at the end. So in doing so, we're not actually swapping two values. Well, we are swapping values, but we're only swapping it down, but we'll keep track of what's where. So let's see. Let's add it here. So the only logical place to do the comparison, I believe, should be here. We'll do comparisons plus. There. And I believe that's our entire algorithm. So here you can clearly see there's one loop to the numbers, and then this one, it's always going to be some subset of the numbers, so some kind of n minus 1, but it's still going through the entire list at worst case minus 1. So we get worst case of n squared, average case of n squared. Best case is a little harder to show, but basically if the list is already sorted, if we're already here, there won't be anything to actually swap. So you'll check. So you'll do these two. You'll check these two. They're already good. These two, and these two, and it didn't have to go back down the list. So it's it ends up being it ends up being linear time. So n, and in that case, it's actually n minus 1 is the actual time. So 1 minus the number of values. So yeah, so that's really all there is to it. So its space complexity is 1. We don't create a new array or anything. What we're given is what we use. It's also stable, so if you have the same values inside, so like if you have two 3s, for example, the 1 3 will always stay above the other 3, so everything's still stable. Let's open my Excel sheet. Let's go over to program now. And this out. Insertion sort array. Insertion sort with comparisons of array. All right, so there we go. So that should be our algorithm. So let's check if it works. I opened Excel in the background here as well. I'll go ahead and let's make sure it works first. Click the correct build. Let's give it 1,000. Do we want to accept duplicates? Yeah, no. We'll just use the default settings and run. So that was 1,000. So we got 122. So let's compare the other two sorts. For 1,000, what did we get here? Significantly slower. I'll go ahead and spoil it, but we'll see that this one's going to be significantly slower as well. This one's the slowest of the 3 per 1,000. And that's pretty much what you're going to see in general, is even though they're all n-squared algorithms, insertion sort's quicker than the other two because it's just going through the list fewer times. And it slows down a lot as you get bigger, but not as much as the others as you get bigger. So what you'll find in a lot of the built-in search algorithm or sorting algorithms in different languages, well, a lot of them actually use insertion sort when it's on a smaller number of values, and use something better when it's on a bigger number of values. I actually haven't checked if .NET does that. .NET does, but I know some other languages do. There, I'll Google it really quickly. Okay, so in C#, Array.Sort is used a hybrid called introspective sort. So what it does is it does insertion sort if there's fewer than 16 elements, so very little, so it doesn't have to worry about anything else. Anything above that, it uses quick sort for most usual cases. Quick sort is something called recursion, so if the recursion gets too big, it falls back to one other type of sort called a heap sort, and we'll look at both of those in the future. So it does use insertion sort, so I was right. All right, so yeah, so this one's the first one that you actually might see occasionally here or there, or you might use some, or these other two you probably aren't actually going to use anywhere. So tell you what, let's go ahead and grab the data and we'll do some comparisons. So we'll do this one here and here. What we're going to do is we're going to run this and fill out the table here. So let's move or copy, move to the end, create a copy, and we will rename it to Insertion Sort. So we will remove these. Remove these. Okay, so we're ready. So I'm going to take the data and I'll fill out the table in the background while this runs. So we'll begin 10. We get 0.5, 0.2, and 0.26. That's the kind of level that's the algorithm that .NET actually uses. 100. That is a huge maximum. Very first one. 3. Here, let's run that one more time. Let me check that. That'd still be huge. Okay, so it has a huge one run there. 390.3. Again, that's an outlier, so it should be excluded, but I'm not excluding it, but it is an outlier. The first one's also really slow as well. As we've seen, there's always a startup time, and we're actually cutting that one out. We're skipping the first outlier. 224, 116.8, 121.78. Next, we have 2,000. I don't know why I want to call that 20,000 every time I see it. .32. Okay. So 5,000. Three 331.2, 2629.4, 2716.34. There we go. 10,000's next. So this will, after this algorithm, the next one we look at will actually, I think you won't see any, you'll see everything here probably being a lot quicker than any of these algorithms do. All right, there's that one, about 10 seconds or 10 microseconds. About 40 microseconds. There we go. We'll do 50,000 next. This one here, you can really see it starting to take a little bit of time. It's going to be somewhere around 200 milliseconds. Two four two 1.38. There we go. All right, finally, the slowest case. So look at that one. These are running about a second apiece, so this one will take about 100 seconds. So just on the comparisons as of this moment, the we're going to see that it very much looks like a n-squared algorithm. So the graph already looks as we expect. So I expect that we'll see once this one finishes, we'll see the same thing. So the important bit here is that we'll as we look at the numbers here, I think we'll see that in the lower ones, this one so outperforms the other three or the other two. It just makes sense why you would ever use the other two. I think for the later ones, I think there's not going to be a ton of difference between them. I think yeah, I don't think we'll see much difference at all once these numbers actually come through. Yeah, look, there's 60. So yeah, it's going to end up about 990, I think. So the next algorithm we'll look at is quick sort. So it gets its name because you'll see it should be pretty quick compared to these. In fact, we may even have to bump the number up on up the million number I support. All right, there we go. So there's those numbers. We'll hurriedly grab the comparisons count. Let's hold off. Let's do one more thing. Let's just look at this one just a second. Let's say we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this ran in, it averaged 0.26 a minute ago. So let's see what this one. That doesn't matter. This one averaged at 1, but it is having to do a little bit of creation work. Yeah, first one was really slow. Let me save that off like we did before. Let's do like this. Where do we actually grab the number of here? So here we'll just say original array equals 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We'll do it like that. Now let's run it. There we go. And there, that is 14 or 0.14. That's almost half of what it was before. And what you'll see is, in the best case, it'll be a lot quicker. I wish there was an easy way to make this bigger. Yeah, I could probably generate it quicker than this would be. Yeah. We'll do it like this. Let me delete that last one there, and let me grab these. I'll have to do one fix there, but let's do it like this. 0 or 0 0, 0 1, 0 2, 0 3, 0 4, 0 0 5, 0 6, 0 7, 8, 0 9, and then we'll stop there. So we'll just copy this, and now just grab these. We'll do what's the keystroke? And that's being stupid. There's some keystroke here that lets you select values, but for some reason I cannot remember what it is. There. Okay, it's Alt, Shift, and period. 4. Still have the first one to deal with, but there, we'll do 5. Six. Yeah, this would have been quicker to just generate this, I think. And then sometimes it just does that instead. Yeah, whatever that's doing is dumb, because that's the exact same keystrokes I was pressing. 6 6 6. I want to show how much quicker this was on a bigger number, but this is taking off a long time. Yeah, I don't know why it's doing that, because that's the exact same keystrokes I was pressing a minute ago. Let's do it like this, I guess. We'll do it like this, and then over here we'll just make this 7. Eights. Nines. And 100. Yeah, there's got to be a quicker way than that. Oh, that'll work. Now if we run this real quickly, that 1.1 seconds is about 1/10 of the speed of 100. I'm not even going to try 1,000. I guess the easier way to do that would have been to already sort it. So we would have been to do this. But yeah, let's do that real quick, and let's do 100,000 really quickly. And they're significantly faster, and that's because it's doing basically the optimization for bubble sort. In fact, when we did bubble sort with the early exit, best case we got 50 or 60 macroseconds, so even a little faster than this. So we're running on very similar speeds basically though. So let's see. All right. Yeah, let's go ahead and grab the rest of the data at this point. I should have just sorted this to begin with. That would have been quicker. But let's grab the rest of the data and then we'll do our comparisons. So here I'll run this pretty quickly. 30. And yeah, I don't know what a good benchmark for comparisons here are actually. Because here they're more random than the other algorithms. The other algorithms are more predictable. This one's pretty random as far as how long it's going to take because it's just going through the list and inserting. I guess basically though the other side should be an upper bound. So the generic ones I've been using, I think they would be an upper bound, so it should be something lower than that, and we're already seeing quite a bit lower. We want to make a change here. Let's bump this to 2. That's just to keep the speeds pretty quick for the rest of these. $10,000. Just going to grab the number now. 20,000. Yeah, we're pretty easily beating our benchmark. 50,000. And 100,000. Yeah, beat our benchmark on every single one. All right, so here are our graphs. So the first thing to notice is that looks very much like the N-squared algorithms we were looking at before, with the exception of that one, but looks like the growths were similar. In fact, seems like it was quite a bit quicker as well. And in fact, it was. So the average case here was that. So 975,000. This was almost 1 million more than that. This one's over almost 10 million or 11 million more than that. Even with our early exit, it was still not significantly faster. So yeah, so I'd say insertion sort pretty handily wins. Notice for all the comparisons, every single one's less than the benchmark, so that makes sense. So it's performed better than the worst case, basically. There. Here, let's do one more check. So let's see. So best case, I think should be. I think it should be. So if we do a size of 10, I think we should get 9. And we do 9 comparisons. So best case, it had to go through the list and it checked all the values except the first one, and it didn't have to do any swaps, so we got 9 comparisons. That's all we got. So yeah, that's best case. So yeah, so that's pretty much, that's the insertion sort algorithm. Performance-wise of the first 3, and these are pretty common first 3 because they're all n-squared algorithms, but as we just seen there, this one pretty handily outperformed the other 3. Bubble sort's usually the one that's considered most intuitive. I personally think selection sort's the most intuitive. Insertion sort's the one that performs the best. So we'll go ahead, and we're a little early, so we'll go ahead and stop here. For next lesson, we'll move on to quicksort. So quicksort's another very common algorithm, and we'll see it performs differently than these. And it's the first one that's, in the average case, isn't n-squared. So these others have not been n-squared in best case, but in average case, they've been n-squared. The next one won't be. We'll go with that next time. So we'll call it there. So thanks for watching, and have a wonderful rest of your day.